All right, so what we're going to
we're
look
going
at
to
now
talk
is the
about
comparison
the
test.
next
So in the
type
back
of
of
series
your mind, what
test,
you want
which
to
are
keep
the
track of are
comparison
the different
test.
tests that we have.
So in the back of your mind,
the
one of
most
the basic
basic ones
ones
are
your P
P
series.
series.
That's one of your basic tests. Remember, if it looks like 1 over n to the p, if p is bigger than 1, it converges. Then you had the geometric test, and it looked like AR to the n. And if the absolute value of r is less than 1, then it converges. And the other one is your nth term test for divergence. So usually you can look at them and kind of get an idea of what you think you should compare them to. So there's two different types of direct comparison tests. The first one is your direct comparison. Okay, so when looking at the direct comparison test, what you have to do is do a bound. So right here, if I'm looking at AN, and I know that BN is bigger, if AN diverges, so if this one diverges, then we know that anything bigger than it would also have to diverge. If we have the different inequality and we start here and we know that this one converges, then we know anything smaller than it must converge. But what we don't know are different things like if this one converge, what does this one do? Because it's bigger, it could converge or diverge. If this one diverges, I don't know anything smaller than it. Okay, so we got to find a bound. So the direct comparison test all works on trying to find a bound. So looking at it here, this looks like a geometric, but it's not a geometric. So I'm going to compare it to a geometric. Now I'm going to make sure that this inequality holds. So one thing you can do is flip both. So you flip do the reciprocal of this, change the direction of this, do the reciprocal of this. And that makes it very, very clear that it is in fact a bound. Since this is a convergent geometric, anything smaller than it would also converge. The second one, we can see we have a p-series here. And it's comparing to a divergent p-series, so I hope it's bigger than a divergent p-series. And again, doing the double flip, you can see that that does diverge. Since it's bigger than something that diverges, therefore it diverges by DCT. Now, one thing we got to know is kind of have an idea of what we think things will do. 1 over n factorial. I know n factorial grows really, really fast. So 1 over n factorial is going to go to 0 really fast. So I think this bound holds. And it doesn't have to hold right away. It just has to hold after some point. And I think with after like 4, it works. Because 4 factorial would be 24. 4 squared is 16. So I think after n equals 4, it works. And then this is a very common thing that we do here, is that you're going to bound sine or cosine. The biggest it could be is 1 or negative 1. So I know it's less than or equal to 1. And same thing with cosine. Another common bound we're going to use is the arctangent. The arctangent is less than pi halves. Because remember, it's lazy tangent. It's on its side because it's the reciprocal. Now, direct comparison test really only works if we can have very simple functions that we can compare it to, because showing that that is actually a true inequality could get difficult. So the next one we do is limit comparison test. And what we do there is as long as what you compare it to, the limit of the ratio is finite and non-zero, then they converge or diverge together. Okay, so you're kind of going to do the same thing we did on the last one. Here, looking at this, it would be hard to show that that was less than something. But what I do know is when I look at the degrees, it's basically behaving like 1 over n cubed. 1 over n cubed is a convergent p-series. So what we have to do is look at the ratio. So you're going to take the first series, divide it by the one you're going to compare it to, which means you're going to multiply by the reciprocal. And notice here that the whole point of this is that the degrees are equal. If the degrees are equal, it's the ratio of the leading coefficients. And as long as this is finite and non-zero, these series change at the same rate. Since this one converges, the more complicated one will also converge. If you tried to compare to something that wasn't changing at the same rate, then your limit would be either 0 or infinity. So same thing with the second one. Unfortunately, it's the same p-series that it compares to. Okay, so getting a little bit harder again. So here we're going to compare this one. You see how it's got 1 over root n. So the limit's finite, non-zero. And then here, comparison, looking at those biggest degrees on the top and bottom. And again, it's comparing to a harmonic. Harmonic diverges, so therefore it diverges. Now, when the series get more complicated, again, always paying attention to growth rates helps. So thinking about the growth rate here, this geometric 3 to the n, exponentials grow faster than a polynomial. So immediately I know this diverges by nth term test. But you can also do a comparison. So I could have compared to this, which I think most of us would have seen, and then the limit would also be finite, non-zero. Which of the following statements are true about this? Okay, so when I think about natural log of n plus 2, I know that grows very, very slow, so I'm going to expect it diverges, okay? But just looking to certain things, this says it's going to converge when compared to 1 over n. Well, every time I do a convergent with a comparison, or a divergence, when you ever do that with a comparison, they either converge or diverge together. You never get the opposite. This one diverged, so this one can't converge. It doesn't make sense. Right here, this one is 3/2. That is a convergent p-series. I don't know why I said divergent there. But that converges. And then we have this one right here. That also, this converges. And then this one right here, compared to harmonic, diverges. So this is what I expect it to do. I expect it to diverge, and my harmonic diverges. And I think if we want to show that with direct comparison tests, we need to show that this is bigger than 1 over n. Because if 1 over n diverges, then anything bigger than it would diverge. So I'm going to do the double flip. And it's still harder for us to see, so what I'm going to do is exponentiate both sides. And I think that makes it very clear that exponential is definitely going to be bigger. So D, it diverges. Which of the following converge? So this one's like p equals 2. The next one's like, that's nth term test for divergence. P equals 1. And geometric diverges. And again, just another comparison. This is how AP loves to do the DCT test. So they tell you AN and BN are both bigger than 0, which is important because if we had negative values, then we'd worry about it going to negative infinity. But this is saying that everything's positive. We're only worried about that right side. So if AN diverges, then we know anything bigger than it diverges. Okay. Again, just the limit comparison test is the best way to do this. You can see right here, if I compare it to that, then that would be your limit. And again, it's another geometric, so we're going to compare it to that. This is nice and easy to get with DCT. Divergent p-series, convergent p-series, convergent geometric. And again, these are not the test. I didn't show the either the direct or the limit comparison test. I just kind of did a mental guess, or mental. Don't worry about 17. That's an extremely hard problem. We're not going to worry about that one right now. 17, I still need to look at it. I couldn't remember why this AN is bigger than BN. Doesn't. I need to think about that. Let me go back to that one. Diverge. If AN diverges, BN diverges. And then here, this is telling us something about the limit comparison test. It's finite non-zero. So we would know that if A converges, B converges, because remember the comparison test are the BFFs. They do each, whatever one does, the other one does. And if this one diverges, the other one diverges.